Probably a good move. Okay. So for the brave ones, for us, we are on chapter 4. We're going to finish chapter 4 today. It's going to be great. So, this is the intro, steady state response performance. So, after the transient response has settled, so remember last chapter we worked on the transient response performance characteristics like rise time, peak time, settling time, percent overshoot, that type of stuff. And we learned how to find for a given response what those are. Exactly in the case of a second order system or a first order system with no zeros. And then using numerical simulation techniques for everything else. So, in this chapter, we're concerned with what happens once it reaches steady state. It may or may not be in a desirable state at that point. So, it might respond fast, but if it doesn't go to the right place, that's really not desirable. If the response asymptotically approaches any state other than that commanded, so remember we're doing feedback control, so if we command it to be, 20 psi and it ends up being 19 psi, that's not what we were going for, right? It is said to have steady state error in this case, so we call that steady state error. After it's settling down, it's still something that's not what our command is. These arise from three primary sources, these steady state errors. The first is nonlinearities, like backlash in gears. We won't explore this one. It's common, but it's also a whole topic to go into. 2, disturbances, like those from the environment. And 3, input, command type, and the plant dynamics. So if you tell it to go to some constant value, that would be a specific type of command. But if you tell it to follow some path, so if you change with time what your command is, say linearly or sinusoidally or whatever you want to do, then the ability for the system in steady state to track that depends on what you've commanded it to do. And it also depends on the plant dynamics as well. So we're going to focus our attention on item 3, so this last one, the input command type and the plant dynamics. But it turns out that you can frame the second type of steady state error, which is the second contribution to steady state error, disturbances, in a similar way. So if we focus on the item 3, then we kind of get item 2 for free, and we can do a very similar analysis for item 2. So let's just go ahead and jump right in. So there's only one lecture in this chapter, 4.1, steady state error for unity feedback systems. It is actually uncommon for a feedback system to be truly unity, meaning that when we feed it back, so here's a block diagram, when we feed it back, we don't have any transfer function or any gain or anything like that in the feedback loop, in the feedback path. It's uncommon for a system to be actually like that. So you might think, oh no, this is another purely academic exercise, this doesn't really matter, real systems aren't unity feedback. But wait, non-unity feedback systems can be refactored, rewritten, and evaluated in terms of unity feedback counterparts. So say you have a system with feedback transfer function in it. You can use the same analysis we're going to learn in 4.1 if you reshuffle that mathematically into a unity feedback system. So it's not, it's totally applicable to all systems that have even non-unity feedback. So even though we're going to focus on unity feedback, And I have you a reference here to NICE section 7.6, where you can find a description of how to do that transformation. It's not too hard. You just have to understand the steps. So, first we recall the final value theorem. I'm kind of assuming that you've seen it before, but you may not have seen it. So we'll go over it in 2 sentences. It's really not that bad. So it's just very handy. Let f of t be a function of time that has a final value. So if you took the limit as t goes to infinity of f of t, you get f of infinity. Okay, so that's the final value. Then, from the Laplace transform of f of t, which we typically will call f of s, the final value is, so the f of infinity, the time domain value of the function little f at time infinity, is not only equal to the limit as t goes to infinity of little f of t, it's also equal to the limit as s goes to infinity of s times f, the Fourier transform of s. So you can find the final value, which for us is going to be the steady state value, right, of a function of time if you know its Laplace transform, and you say multiply by s and take s to 0, which is great because if we have a Laplace transform representation of, say, the error, which is what we're going to develop, then you can find what the final time domain value of the error would be without having to actually solve the inverse Laplace transform. We kind of like to avoid doing an inverse Laplace transform if possible because that's usually the toughest part. Taking Laplace transforms is typically easy. Inverse Laplace transforms can be harder. So this final value theorem is going to give us a shortcut so we can avoid doing the inverse Laplace transform. So now all we need is to express E of s, so the Laplace domain error, in more convenient terms. So if we have the error as a function of s, the Laplace domain, we need to find it in more convenient terms. So we need something that we can I guess, analyze a little bit. So for the analysis that follows, we combine the controller and plant G equals G1, G2. So I'm going to combine both of these into a single transfer function, and I'll call it G of s equals G1 of s, G2 of s. So you could represent it as one block G if you wanted to. From the block diagram, we can develop the transfer function from the command R to the error E. So typically we're trying to find the closed loop transfer function, right? From the command R to the output Y. That's the closed loop transfer function. So when we put in a command of 20 psi, we want to see the output Y go to actually 20 psi, ideally, right? But in this error analysis, we're interested to find the transfer function, not the closed loop transfer function, but the transfer function to the error from R. Okay? So if you command something, how much error are you going to get is what that'll tell us. So we can write, remember this block diagram just represents algebraic relationships. So we can say that the error is equal to, from this block, from this summing junction, what is it equal to?
R minus the feedback.
Yeah, it's R of s minus the feedback, which is, if you go all the way back, y, right? Y of s. Okay. If you plug in the expression that this, remember, combined block gives you, which is that G operating on E gives you Y, right? So R stays the same, R of S. minus, we can replace y with GE, right? G of S, E of S, and now we've eliminated y. We have E in here, we have R in here, and we can solve now for E, which we need to do by moving this term over to the left-hand side, factoring out E, and dividing over whatever is left. So E of S equals, what's left on the right-hand side is going to be R, but we're going to pull R out. So R of S. Nothing ends up in the numerator besides just R, so we'll have to put a 1 there. And then when we factor out on this side, E just has a factor of 1 plus G, right? So that is an expression for the error. And if we wanted to, we could, of course, go the full transfer function representation. That was just actually a solution for the error. If we wanted to, we could write it as E over R equals 1 over 1 plus G, right? By dividing both sides by R. That's fine too, either one. I did write transfer function here, so I should actually finish with this. Although, this is the expression that we're most interested in because we're going to use the final value theorem on it in a second. So, given a specific command R and forward path transfer function G, we could take the inverse Laplace transform of E of S to find E of T and then take the limit, right? So this is a solution for E of S. If we can take the inverse Laplace transform, we have E of T. Then we can take the limit as time goes to infinity, find what the final value of the error is. But we're going to use the final value theorem shortcut instead. However, it's much easier to use the final value theorem. So E of infinity, little e, time domain E, is equal to the limit as S goes to 0 of S times E of S by the final value theorem. We plug in our expression for E of S that we just developed. We have the limit as S goes to 0 of S times, or actually I'll put the S in the numerator, S divided by 1 plus G of S. And we have one more term, right? E's got this R of S also. So I'll plug R of S, I'll just leave R of S for now as it is. This last expression is the best we can do without a specific command R. So G and R, if we know what they are, we could plug them in and we could evaluate this, right? But we're going to try to do something that's a little bit more general, using the form of G and the form of R, canonical forms of R. So 3 different commands are typically considered canonical. The first is now developed in detail, and the results of the other 2 are given below in the table. So first, consider a unit step command, which has Laplace transform R of S equals 1 over S. So I said there are 3 canonical inputs or commands. One of them is the unit step, and the other 2, it might not surprise you, the Dirac delta impulse, and then the ramp function. So those are the 3. We're going to focus on unit step and do the full derivation for that one. The other ones are really similar. So if you do the unit step command, its Laplace transform is 1 over S. How do I know that? Well, it's in the table, right? Or you could do the integral if you wanted to. But the 1 over S is in your Laplace transform table. It says for unit step input, 1 over S is the Laplace transform. So we can plug that right into this expression, right? So that's what we do. We say e of infinity, our steady state error, is equal to the limit as s goes to 0 of s over 1 plus g of s times r of s, which for a unit step function is 1 over s. We get this nice cancellation that occurs, so the s's cancel, and we get the limit as s goes to 0 of 1 over 1 plus g of s, which we're going to define a factor kp that we're going to use in this expression. So 1 over 1 plus kp. So if you take this limit, you can actually distribute the limit throughout this. So if you take the limit as s goes to 0 of 1, it's still 1. Same with this one. And g of s is the remaining term to take the limit of. So kp is what we define the limit as s goes to 0 of g of s. It's called the position constant, kp. The name is barely motivated in my opinion. I think it's confusing to try to read too much into that name. It is just that definition. The limit as s goes to 0 of g of s. If kp is large, what happens to the steady state error here? So say kp is 500. Yeah, it's 1 over 501, which is a small number, right? And if it gets infinitely large, kp gets infinitely large, the steady state error is 0. So kp, this limit here, is what determines for a step input how large the steady state error is going to be. If kp is small, the steady state error is a finite constant. So like if kp is like 0.2, it's 1 divided by 0.2, or 1 divided by 1.2, right? The form of g of s has implications for kp. So since g of s is what we're taking the limit of, it affects kp. So g of s has a factor 1 over s to the n, where n is some non-negative integer. N might be 0. So if we had some transfer function g of s, and it was equal to, some polynomial fraction in s here, so polynomial in s to the blah, plus blah, 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 s to the blah. Thanks. You need that on Friday the 13th, apparently. I don't know why. We just like to say that. S to the, it's to keep, evil spirits out after you sneeze. Friday the 13th is super important. So, 1 over s to the n. If you can set n to 0, that means that this would just be a factor of 1, right? So what we're saying is you can always have a factor of 1 over s to the n as long as you can make n 0. Holds true for every transfer function. But you might be able to factor out 1 or more s from the denominator, right? So, for instance, the denominator might be s cubed plus 4s squared plus 3s, let's say. You can factor 1s out of that denominator, right? We're assuming that you never like dividing by s. You factor it out. So you can factor 1s out. So that would mean your n is 1, right? If this term wasn't there, say, in your denominator. You could factor 2 s's out of that, right? So you could have s squared and then s plus 4. So you can factor 2 out in that case. So the number you can factor out of the denominator is important. This factor of 1 over s to the n is important. Since we are concerned about what happens to g of s when we take this limit as s goes to 0, this factor is of particular importance. If n is greater than 0, what happens to g as you take s to 0? So when s goes to 0, it becomes 1 over 0, which goes to infinity, right? Blows up. So g of s, no matter what finite thing this comes out to, because it will be finite in that case, you are going to have g of s blow up to infinity, which means that kp is infinite, and if you plug kp in here when it's infinite, our steady state error is 0, right? So that's ideal. I mean, in terms of steady state, we want to have these factors of 1 over s in our transfer function. We call the transfer function 1 over s an integrator, which is the inverse of the transfer function s, which is the differentiator, right? So we want, for better steady state error performance, we want more integrators, okay? More factors of 1 over s. And if you have none, if you have no factors of 1 over s, this comes out to be some finite number when you take s to 0, right? It's going to be whatever the last coefficient here is in the denominator, and then whatever the last coefficient is in the numerator divided by each other. When you set all the s's to 0, that's what you're left with. So in terms of steady state error, we're trying to get more integrators in the transfer function. At least one integrator in the transfer function. For a step input, you got to have at least one to go to 0 steady state error. Okay. We didn't solve for E explicitly then, so we didn't actually solve for E. All we did was we know how many integrators are in G, and we can find out a lot. So all we need to know is Command R and the number of integrators n in the forward path transfer function G. We call the number of integrators the system type, okay? System type. N is the system type. So a type 0 system would have how many integrators? How many? 0. 0 integrators. How many? What's the type of a system with a factor of 1 over s to the 49? 49. Yeah.
Sure.
Jeez, man. No. Yeah. I'm just messing with you. The steady state error for other commands and system type can be derived in a similar manner. The results for the canonical inputs are shown in table 4.1. So let's look at this table for a minute. Actually, all fits on the screen. So, we call, oh, by the way, Kp is called the position constant. It's one of 3 named static error constants. So this is the one we've already seen, Kp. There are also 2 others, Kv and Ka. And they correspond to different command types. So unit step input, this first row is the one that we already did, right? So let's go down this row, make sure we're familiar with it. So for a type N system, like we don't know, it's just a general case, right? So we don't have a number of integrators yet. The error constant is just the limit as s goes to 0 of g of s. So this always applies every time. And the error, steady state error, is 1 over 1 plus kp. So you can compute that, and decide what the steady state error is. If you have one of these typical cases, which is you have either a type 0, a type 1, or a type 2 system, these are the most common, then you can go through this table. So if you have a command that's listed here, so either a step input, a ramp input, or a parabolic input command, and if you have a type 0, type 1, or type 2 system, we're going to work that out. And I'm actually going to fill in the rest of this table for the remaining bits here. So when you have a ramp input, a ramp command, and a type n system, just in general, okay? So whenever you have a ramp input, this is your steady state error, 1 over kV, where kV is called the velocity constant. It's one of the static error constants, and it's defined to be the limit as s goes to 0 of s g of s, okay? And this mostly just comes into the fact that as you do more of these, your R value. So let's look up. We have time to look it up. Let's look up what is the Laplace transform of the ramp. Maybe somebody knows it off the top of their head. No? Come on, guys. Jeez. Right. I'm just making stuff up. Let's see. Yeah. This is my local copy. Text. Oh, there's my drawing of myself. That's cute. Did I do it in the control? No, it was a dynamic systems textbook that I gave that. And Laplace. Did I not do a Laplace table in here? If I did. Fourier transform. I never gave you a Laplace transform table in here, apparently. Sad face. Oh well. I'm not going to go through the derivation though, because it wasn't very instructive. I can't do that. All right. So, in any case, we have our error constant, of course, is kV, right? So we take the limit as s times g of s for a type 0 system. I wanted to motivate this s, but if you look up a Laplace transform table, it'll become clear why that s is there. All right, type 0, error constant, kV. We're gonna have our g of s has no integrators in it, right? So that's what type 0 means. So no integrators in it. So as s goes to 0, there's not going to be anything in g to cancel that s, right? If there was one integrator, we would have a 1 over s, and they would cancel. But there's nothing to cancel it. So as s goes to 0, kV is going to go to 0, right? And that's pretty disastrous for our steady state error, which is 1 over kV. So that's going to be infinite. Our steady state error, if you have a type 0 system and a ramp input, sucks. Okay? It never catches up. So what we're seeing here is, like, we've got a command that's linearly increasing with time, like this, and then we've got this kV or this response that's like never gonna catch you. It's just gonna like get further and further behind as time goes to infinity. It's gonna grow and grow. The difference between them. This is gonna be the error, right? And that is gonna grow. It's harder to keep up. So if we had a type 0 system with a unit step input, that would look like this step input command, and then we're going to have this thing respond, but it's never going to quite get there. It's going to have some finite difference. But that stops for a step input. But for a ramp input, that just keeps going, right? They just keep diverging. If you're saying like I want it to be 20 psi now, and then I want it to be 30 psi a second later, and then 40 psi the next second, 50 psi the next second. A type 0 system can't keep up. But if you add an integrator, so type 1 system, what happens? So let's see. Our g of s is now going to have a 1 over s in it. It's going to cancel that. S there, so s and 1 over s will cancel. You have limit, as s goes to 0 of g of s, which will be some finite number, right? So when it's some finite thing, I just put the error constant there, so kv, something finite. And then you have to compute the steady state error. It's going to be just 1 over kv, right? Whatever that is. This could be 5. So in this case, you have an integrator. Your response is going to, it's say it looks like this, and it tries to catch up, but it never quite does, but it's some constant offset. It doesn't grow with time. It just stays, it lags behind. So every time you say if you say I want 50 psi, it's like, well, I can give you 48 psi. And then it's like, I want 60 psi, and it's like, well, I can give you 58 psi. And so it's always lagging behind, but it's at least not growing. The error's not growing with time. Finally, if you add a second integrator, so a type 2 system, you're going to have one of the s's canceled, but you're going to be left over with an integrator in the denominator of your g. So as you take that limit as s goes to 0, your kv goes to infinity, right? And so that's the error constant. And then your steady state error is going to be 1 over infinity, which is 0. Okay. Now we go one step further. Now we're running away as we're running away, right? The parabola command is like follow me as a parabola. So I'm going to just like really take off, right? So if it's of this form, we have a type 0 system. What do you guys think? Are we going to be able to keep up with a type 0 system? No. It's going to get even worse, right? So, I mean, you can't get worse than infinite steady state error. So that's what we've got, infinite steady state error again. Because you've got 2 of these s's here and nothing to cancel it. If you add a type 1 system, if g is type 1, one of those s's cancels, but you still have one s in the numerator. Still bad news, 0 and infinity. You can't catch up. It just keeps diverging away from you. Now, if you go up to a type 2 with 2 integrators, you can at least make it finite in this case. So 2 integrators cancels these 2 s's, and we get limit as s goes to 0 of g of s. So it's something finite with error constant Ka, which is called the acceleration error constant. So position, velocity, acceleration. It's because there's some vague analogy with, because you're integrating each one. So Ka, and then your error constant is 1 over Ka, right? So you'd have to go to a type 3 system if you wanted to get steady state error to 0 for a parabolic command. Okay. Woo! That's the whole table. We did the whole table. So yeah, that's pretty much that. Now, if we are feeling pretty confident, we can just go ahead and hit up an example. Are you guys feeling good about it? We have 15 minutes. Just slowly work our way through this example. Let's do this. So we have a system with a forward path transfer function given by G. So first of all, what type is G? Type 1, right? How do I know it's type 1? Yeah, so you can factor out a single s from the denominator. You can't factor out any more s's from either of these, right? So this would end up giving you, if you divided 1 by s, you would be 1 over s, right? So you can't factor anything else out. So we're stuck factoring just 1 out. We have a type 1 system. And we're going to give it 3 different commands. And we're going to find out what are the steady state errors for those 3 different commands. So if we give it something easy, this is the softball, right? Step input. This is like, hopefully you can handle the step input. This is the t-ball of commands. Okay, just the step input. So if we've got our, so R1 gives us, if we look up in the table, we're working with a type 1 system, so we're working in this pair of columns here, right? The first input is unit step, but it's multiplied by 2. So that's something we haven't seen before. We've got to figure out how to handle that factor of 2. Essentially, the factor of 2 just multiplies through to the error. So that's how you handle the factor of 2. But we have a step type input. A type 0 system means we need to compute the error constant Kp for, well, if it's a type 1 system, we already know, right? What's going to happen? The error is going to go to 0 for a step input. So if we wanted to, though, just be sure, we could compute Kp, right? The limit as s goes to 0 of g of s. And what happens? So all these s's, so 0, 0, 0, 0, 0, right? All those goes to 0. And oh wait, 0, so it wipes out the entire denominator to 0. And something finite 10 times 4 in the numerator. So we end up with something infinite, right? So that tells us that our steady state error has to be equal to, it's going to be scaled by 2, which is laughable in this case. So 2 times 1 over 1 plus Kp, which the 2 didn't help the numerator out, did it? Still went to 0. Steady state error of 0. So for this system, if you give it any sort of step input, even if it's 2 or 10 or whatever it is, it's going to have 0 steady state error. And we knew that if we would look at in the table, we would say, oh, it's a type 1 system, and it has a unit step input, so its steady state is going to be 0. You can scale whatever's in there by whatever the command is scaled by. So if you scale u of s by, or us by 2, you scale 0 by 2, you still get 2. So you still get 0. You still get 0, I promise. 0 times 2 is 0. Even today, on Freaky Friday, the 13th. Guess what my number was in sports?
Wow.
Trick question, I didn't play sport. No, I did. It was 13. Okay, R2. We have a ramp, right? So it's a ramp input, and it has a slope of 6. So we've got a type 1 system. We could look here and say, oh, look, it's error is 1 over kV. We got to scale that by 6, and we'll be good. But let's go ahead and compute kV just for the hell of it, because we need to do it anyways, right? So limit as s goes to 0 of s g of s. So with this s in the mix now, because we have a ramp function, this s will get canceled. So we're going to have something finite. What happens when s goes to 0 in the rest of this transfer function? What's left over? All the s terms go to 0. We get 10 times 3 times 4, and then we get 1 times 5 in the denominator. So 1 times 5, 10 divided by 5 is 2. So 2 times 3 times 4 is 24, right? I think. Is that what you guys think? Okay. I try not to actually do math. Okay, so 24 is what I got last night too, so that's good. It's very unlikely that I'll do it wrong twice, except for when I do. Then it's pretty likely. Okay, so we have KV. We know that our steady state error is going to be 1 over KV, but it's got to be scaled by whatever we scaled the ramp by. So steady state error is equal to 6 is what we scale the ramp by, so 6 times 1 over KV, which is 24. Well, I'll just write KV for, we computed it here, 24. So this comes out to be 1 over 4, right? Cool. R3. So notice this got worse, right? Went from 0 steady state error to finite steady state error. We're expecting that if you put in a parabola, we're going to have something bad happen, right? We already know that. But let's compute Ka just to see. We're expecting Ka for a type 1 system to be 0 and the steady state error to be infinite. But just for demonstration purposes, let's plug it in. Limit as s goes to 0, s squared g of s. And we have a problem, right? Because the s, one of them cancels, so we're left with an s in the numerator. And that s in the numerator, if it goes to 0, the whole thing goes to 0, right? So our Ka is 0, and our steady state error is going to be, so it's going to be infinite, but let's be precise with our factor anyways, just so that this is a little gotcha. The parabola here specifically has a 1/2 in front of it. So if that 1/2 is the normal factor, and what we have is 7, what are we scaling it by? 14, exactly. So 14 times 1 over Ka, which is infinite. So we can't catch up with the parabola with the type 1 system. We knew that already, but we went through and we verified it in this example. So this is like steady state error. This is like all of it. That's why I only gave one lecture on it, because that's the whole thing. You should be able to do all the homework now with this. So, are there any questions on steady state error? So you really, understand how it works. I do encourage you to go through and learn from the fact that, so our time domain commands are essentially being integrated in the time domain here, right? So from 1 over s to t, or from us to TUS to 1 over t squared US, and how that affects what this steady state value is going to be. You can go through essentially this derivation here, And we're going to see something happening with this term that's different when you have the parabola versus the ramp, etc. So I encourage you to do that. Understand well how to use this table because it allows you to find steady-state errors really quickly, right? You don't have to do much, especially if it's 0 or infinity. You don't have to calculate anything. Just look up the number of integrators, figure out what your command is, and then you can look up, is it 0, is it infinite? If it's finite, then you actually have to find your error constant. But, yeah. All right, that's all I got. Have a good weekend.